Okay, well, I took stock of where we are in this course, and unfortunately I was out sick, and I'm not sure how this is going to all pan out on the recordings, but at least for us this year, I'm going to make some adjustments, okay, on the assignments. So, A12, which should have been due 2 sessions ago, is now due today. And then, so what we're going to do is we're going to postpone A13, 2 sessions also. So A13 and A14, but only one question from A14. A14, only exercise 5. Only exercise 5. So these, and exercise 5 is not about any material from the book. Exercise 5 is to read a paper. There's a great survey article that I've posted on our webpage, and it's just to write a summary of it. So nothing big, just kind of like a book report kind of thing. That's all. That's the last question in A14. So exercise 5. So we'll have both of these due when 14 was supposed to be due, which is Monday, October 21st. Due Monday, October 21st. And the other material that's on A14, we're just going to have to skip it this year. So I'm not going to try to cover all the material that I missed because I was out sick. We just won't. Some of that stuff at the end, we just won't learn. I think we were at the point where we were just about ready to, didn't we do the likes Mary, or Mary likes all animals that are not snakes? Didn't we do that one? Okay, so here's our demo. And we had looked at the problem of determining whether Mary likes, what Mary likes. And remember we had a little bit of a problem with that, didn't we? Maybe we should come back. Well, there it is. Let's remember the problem we had with it. We said if we say likes Mary snake, that worked, yeah, because she doesn't like snakes. And if we say likes Mary cat, she does like that. But what was the problem? Do you remember what the problem was? If we said likes Mary what? Remember what happened there? According to this definition up here. Well, you would hope that she likes cat, but can you predict based on this little rule up here what's going to happen?
What is snake, right?
Now we predicted this at the end of the class last time, I think. Or maybe we might not have predicted it correctly, but can you predict it now that we in a little review here? Yeah. So what happens here? What happens here? We say like Mary. What happens? We come up here to. It's the same thing with likes to, but likes to. So will this Mary? Does everybody see this likes will match? All right, we'll go up here. Does everybody see that this likes down here will match this likes? Are you with me? Then this Mary down here in the query will match what? This Mary. Are we good? Then what will happen? This is a variable. What? Do 2 variables match?
Yes.
They do. So this will execute. Are you with me? Mm-hmm. And then what will happen is here is what will equal what? I mean, now this is X match snake, but X and what have already been matched. So what does this make? X is instantiated to what? And also, what is instantiated to snake, right? Is everybody good? Then we do the cut. Do cuts always succeed, or what happens when we do the cut? Does it succeed or does it fail? It always succeeds when we, and then what happens to here? Fail. But now does fail always fail? Yes. And now because we went across the cut, we can't do what? We can't backtrack. So what? So what's this? What happens here? Now can we predict what happens here? No. I mean, yes, we can predict that it's no. Yes, we have no bananas. Yes, we have no bananas. We know that song? You don't know that song? Oh my goodness, that's from some musical somewhere, I think. I don't know. Yes, we have no bananas. We have no bananas today. They're talking about, you know, when you say yes and no. Does anybody here speak German? It's good because they have a yes and a no and a on the contrary. So it's unambiguous when you say yes, whether it means yes, no, or yes, yes. You don't know that? Anyway, we got sidetracked. So that was our, all right. So that was a little bit of review. Now, and what we want to do is we want to explore that problem and see how to explore that problem. Now, let's check this out. Here, the next predicate that we want to look at is different. And different xy succeeds if x and y do not match. Now, let me demo different. We didn't do this last time, did we? Let's say different a, b, lowercase a, b. Now, so what should happen here? You guys, what should happen here? Correct. They are different. All right? And just to show you that order doesn't matter, let's do BA. Okay, just for fun. All right? And what's predict this? Different AA. No. Is everybody good? Okay. So can you program different? If x and y match, then different xy fails. So otherwise, different xy succeeds. So can you program that? I think we used different, didn't we? I think, remember when an ant, no, a person should not be a sister of herself. So they had to be different. Didn't we do an example of using different?
Well, I don't know if we used.
I don't think we used different.
We didn't
but like
use
we
that.
did that.
Yeah. Well, I don't remember either now then. Okay, so anyway, if x and y match, then different xy fails. Otherwise, different xy succeeds. So tell me, what is different? Oh. Different xx. Now what? Okay, I've given you the xx. So what should happen here?
It's crazy. That's a weird.
Well, come on, you guys. I don't hear any solutions pouring forth. Ah, so fail, and then what?
Bang.
How about bang fail?
Okay.
Because if you did fail bang, the bang would never execute.
That's fair.
So the order matters here. Actually, I think we had a discussion about this the other day. Is everybody good on this? Okay. Different XX bang fail. All right? Okay. And furthermore, there's another fact that we need, which is what?
That's it.
Yeah, and well, this is it, but we need the second one. Now, do you see why we need the second one?
Because if it's not X, it's
Because if it's not XX, then it has to succeed, and so it's different anything, and those are anonymous variables. Is everybody clear on this? All right.
Couldn't you write that in one statement? Like,
Actually,
like,
it's not. What a great question. The question was, couldn't you write that as one clause like we did before? So can you tell me what that is? Second version written as one clause? I paid you to say that right then.
There's different XX, bash, fail.
Well,
Um,
would it be XX though?
um,
It would have to be what? It would be XY, right? To do the general, to have it be done in general, but then what would the test, then how would you write it?
X equals X.
X match, yeah, so then you would do X, okay, good. So different to XY if X match Y, bang, fail. Otherwise what? Or what? Because if X match Y fails, sorry, no, fails. Wait,
You think X does not equal Y, it has to succeed.
so what goes, wait a minute. If X match Y succeeds, then different to fails. So if X match Y doesn't succeed, then they are what?
They are.
They are different. So what do we want to have happen here? Success, which is true always succeeds.
Why is that not redundant? Why just not have the or?
Or what?
Well, if it doesn't fail, then it automatically succeeds.
Well, you have to have something after the or.
I mean, yeah, don't have an or. Oh, I get it.
Okay, good. Yeah, ooh, I like the way you're thinking this through. Is everybody good with this? Okay, now, the next thing we want to demo is not. All right? Not goal. Okay? And here's how not goal works. If goal succeeds, then not goal fails. Otherwise, not goal succeeds. Now, let me demo not. So it's kind of like a specialization of different. It's kind of the same idea. So check this out. What should not true be? Now, what does true do always? It succeeds. So therefore, not true should be what? Correct. Yeah? Is everybody with me? And similarly, not fail should be what?
Yes.
Yes. Is everybody with me on this? So how about not, let's do a little more complicated example. How about not X match A, capital X match A. So does capital X match A succeed or fail? So therefore, no. On the other hand, if we do not, and then if we say B match A, what happens? Yes, okay. So can we program up not with us, for us? I mean, can you program up not for us? Remember, goal is something that either succeeds or fails. Goal is a goal. It's not a variable. It's arbitrary variable. It's a goal. So what happens? So how can we program up not? It should be kind of like the different thing, right? Same flavor. Not P if what? Well, what bang fail? P, Yes. Well, yeah, sorry, we changed the letter to P, but yeah, okay, good. So P bang fail. And then what? If we do it as one clause? Yeah. Does everybody see how that works? Now, here's the thing. G prolog doesn't have, actually, I'm not sure if it, no, I'm sure it doesn't have not, because otherwise it wouldn't let us redefine it. So it doesn't have not, but instead it has this interesting notation. So G prolog does not have the not functor built in. It has the equivalent bash plus prefix operator. And you pronounce this cannot prove. All right? And the way it works is like this. the way it works is like this. Cannot, so watch what happens. If I do, let's redo the, if I say, see up here where we said not true? Well, if we do cannot prove true, what happens here? No. And you see up here where we said not fail, and we said yes. Well, cannot prove fail. So watch what happens. Yes. Are you with me? And see here where it says not X match A. Well, if we say cannot prove X match A, that's no, just like it was before. Are you with me? Okay. And if we say cannot prove B match A, that should be yes. So cannot prove B match A, that's yes. So this isn't in the book. This notation isn't in the book, but this is the way gprolog does it. And this is the way you should do it. So we don't have not. But basically it does the same thing as that not. All right? Now here comes a really important point. I'm not sure if I have it on this or not. I don't. A really important point that I'm going to demo right now is that not and cannot prove, both of them. There's a limitation. The limitation is this. Actually, I'm going to write this on the board. We'll use the not version of it, okay? Limitation on query. Limitation on query, not goal. Okay? So here's the limitation. If you have this query and you say not X, X must be instantiated to a goal. X must be instantiated to a goal. All right? And I want to demo a set of errors that's going to be really important in how you think about not versus failure. Or negation versus failure. So check this out. Now, what is our principle up there? It's that it has to be instantiated, because it has to be instantiated to a goal. Because see, notice that this is a goal. Notice that this is a goal. Does everybody understand that X match A is a goal and little b match A is a goal? Fail is a goal, true is a goal. Are you with me on that? That can either succeed or fail by the matching thing. Are you with me? Okay. So look, if we say not capital X, what do you suppose happens? Well, it's not even no. It's not even yes or no. What is it? It's an uncaught exception. There's an instantiation error there. Because the way we define not here, this P up here, when we define not up here, this has to be a goal. If it isn't instantiated to a goal, see like we did here. Look, when we did these nots here, do you see here when we said not X match A, what was this P instantiated to? X match A. Do you see what I mean? It was instantiated to a goal. But because X is not instantiated to a goal, we have this instantiation error. Are you with me? And look, we said in prologue, this is the way you do it in prologue. So what would happen if we do this? That's the exact same thing. Are you with me? Is everybody clear? Has to be instantiated. And look, how about if we say not 5, like this? Is 5 a goal? No. So what's the problem? Type error. Callable. See, notice what I was saying here is complaining. We can't call 5. 5 isn't callable to see. It's the same thing. Look, if we do, remember what would happen when we did in the read eval print loop of functional programming? What did we say integers always did? They evaluate it to themselves, right? But this is a query. What happens if I do the read eval loop, if I do this 5 on here? What's going to happen? See, it's the same thing. Are you with me? So 5 is not a goal. Is everybody clear on this? So X must be instantiated, okay? Now, with that in mind, here's what we're going to do. Let's, with this not in mind, within our toolkit, here is a third version of likes that's going to solve those problems. We're not going to use any cuts. Now tell me, you guys, likes, so this is our third version, likes 3. So likes marry X if what? So now what do we say likes marry X if what? What does she like? All animals except snakes. So what do? We say, first of all, we make sure that X is an animal. Do you see what I'm saying? And so now, and we can look for animal. Now that we have animal as a functor, we can go and we can look, scan our database to check for matches with animal. And now X is instantiated to an animal. And so now what? Yeah, and then what would the notation be for that? It would be cannot, not, or we're going to use cannot prove. So cannot prove X match snake. Is everybody good with that? Okay. So now actually here, so now let's see. Now if we say likes 3 marry snake, if we say likes 3 marry snake, this still comes up a no. And if we say likes 3 marry cat, that says yes. But but now likes 3 marry what? And remember that was our problem before. But now check this out. What match cat? What match dog? She likes cats and dogs, and we can get the whole list. Now do you see why that works here? Because both the cats and the dogs, they work there, and then cannot prove, and then it checks to see if that X that's been instantiated matches with snake. Yeah? Is everybody with me on this?
Because of the animal X first, even if it was snake, animal snake is true.
I know, but this succeeds if this fails, and this fails if this succeeds.
Hasn't it already succeeded in saying animal snake because that was first?
It succeeds. Animal X succeeds, but then X is instantiated to snake, and then it has to go and test this. But this cannot prove is just an implementation of oh, I'm having screen redraw problems here. Right. That cannot prove is just that cannot prove is just this. And if you trace through this, you'll see that it works. Okay. Now here's a third version of different. Okay. So this is different too with no cuts. So now how can we do different with no cuts? Now instead of saying different XX, what are we saying? Different XY. If what? If what? What? Cannot prove. Cannot prove X match Y. That's it. And remember all those problems we had with classification? With all those cuts? Let's try this. Remember we said, I repeated them here so I wouldn't have to scroll. Beat Tom Jim, beat Ann Tom, beat Pat Jim. Class player category. There are 3 categories. Winner, one who wins all games. Sportsman, one who lost all games. Now, how can we do this and improved? So now, class 2, X fighter if. Now who's the fighter? won some and lost some. Yeah, well, Tom, right, I mean, Tom is a fighter, but, I mean, what's the definition of a fighter now using cannot prove? Come. Cannot prove what? Nobody? Anybody? Ferris Bueller. Anybody? Beat X blank, comma, yeah, beat X blank, right, so both of them, yeah, and now there's no cut, right? So if both of those succeed, he's a fighter. But now what happens if he's a winner? Then beat blank X would fail. Do you see what I mean? All right, and now class 2 X winner if, but now comes the, here comes a tricky one. He's a winner if what? Beat X blank, but then what? And cannot, well, no, we don't say fighter.
Cannot prove beat somebody else.
Yes, cannot prove beat anybody. So, yeah.
That anyone beat.
Yeah, so what it would do is it would if beat anybody X succeeded, then cannot prove that would fail, and then he wouldn't be a winner. Is everybody with me on that? And now what about a sportsman?
Beat blank.
Beat blank X, but now also what?
Cannot prove X blank.
Yeah, cannot prove beat X blank. And now with this, look, all of our problems are solved. Look, remember, so now let's do class 2. Let's do class 2, gym. Remember the problem areas? Gym C. Now, I think, who was Jim? What was Jim? Was he the... He was a sportsman. I think this is still going to do it twice. See, because he's a sportsman, it does show that twice. But remember class 2, Tom, winner. Do you remember that problem? Whenever we didn't have the... Remember that one? It was an error. If we did, here, let's do, all right, let's do class. Class, Tom, winner. Remember that problem? It said, yeah, and is Tom a winner? Really? Was he really a winner? No. But now what happens? See, he really is not a winner. So that one was corrected. And how about this one? Do you remember this one? Class, let's do class who winner, all right? So now, remember that problem? It said who equals Tom, it said Tom is a winner, but we know he's not. But now, if we do class 2 who winner, then what happens is, boom, Ann and Pat. So that's corrected now.
So when you ask the gym is it still says sportsman twice?
Yeah, that one we can't correct. Okay, and furthermore, check this out. Do you remember this one? If we did class who category, what did we want to have happen? What do we want to have happen? Have them all. But remember what happened? It just gave category fighter who Tom. But now what happens? And there's no more solutions. But now what happens? If we do class 2, check it out. Boom, 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 boom. Yeah? Okay, so think through all that. Now, our last thing has to do, will help you with your homework for today. Problems with negations. Now, I apologize to the people who are watching this on the video who are not from Malibu, where Pepperdine is, because we have an expensive restaurant in town. It's called Joffrey's. Have you guys ever been to? Has anybody here ever been to Joffrey's? You know where it is? Yeah. Okay. So anyway, it's local. Yeah. Actually, I don't. It's around here. It's Yeah, it's close to Paradise Cove, yeah. But everybody knows In-N-Out. Well, everybody in California, Southern U.S., southwestern U.S. knows In-N-Out. I think it's kind of regional. It's not as big as McDonald's, which is worldwide, but it's a hamburger place. Really good food. The best hamburgers ever, I think. Oh, you guys agree? Do you guys agree? Man, they're just fantastic. Everything's fresh. They slice their potatoes on the site. It's really good. Anyway, they have really good food. So we have good food, In-N-Out, and then we have good food, Joffrey's, but then we also have expensive Joffrey's. Joffrey's is a real high-class place, all right? Okay, now, now we have what we want is we want this rule. Cheap restaurant, right? Now, what should be our rule for cheap restaurant? I mean, we could say cheap In-N-Out as a fact, but what do we want cheap to be? Not expensive. So cannot prove expensive restaurant. Is everybody with me on this? Okay. And, that's our, maybe I'll splice this one out. Ooh, this was a long. Well, maybe I should not have done this. I should have just left it on the screen. I don't know what difference it makes. I might want to scroll back. Now, okay, so here we are with good food, expensive, and cheap restaurant. Now, I'm going to ask you, what should happen if I do good food X? Now, this next demo is really crucial. That is if I do good food X, comma, cheap X. Okay, can you trace through what happens if I do good food X, comma, cheap X? Well, first of all, this good food is going to do what? It's going to first match with this good food, and so X will be instantiated to what? In-N-Out, and it will succeed. Then we'll go to what? Cheap X, but X is instantiated to In-N-Out. Okay, so then what will happen? So then it'll try to go to cheap, so it'll go to cheap. So here it'll be this. But restaurant, or X has been instantiated to In-N-Out, so it'll do what? Cannot prove expensive what? In-N-Out. So it'll try expensive, and it won't find expensive In-N-Out. So what will happen here? So what will happen here? It will succeed. X matches In-N-Out, and there's no more solutions. Is everybody clear on that? What happened? Can you predict this? Can you predict this? Are you just kind of, why did you say fail? Because what's,
Because it'll look for cheap X, and then it'll X is restaurant, and so it'll do X, expensive X, and then it'll make X equal Joffrey's because it'll look for expensive X, and so it'll instantiate X Joffrey.
well, oh man, your analysis was very close to the correct one. The thing of it is that when it does cheap X,
You can't like figure out that In-N-Out is cheap. You're not instantiating X to In-N-Out.
yes.
It can't like produce that on its own.
Yes. Now that is the key insight that I'm trying to illustrate here, because X is not instantiated. Are you with me? when it does cheap X. So when it goes to cheap restaurant, restaurant won't be instantiated. Are you with me? And then when it tries to do this goal, what did we say had to happen to do this not or cannot prove? What did we say had to happen? The goal had to be what? Yeah, it's right up there. The goal has to be instantiated. Are you with me? So look, so if I do this, it's, oh, well, it's not instantiated, so it's no.
But if it's not instantiated, should we come up with that weird error? Because every time it's not been instantiated, it kind of...
Yeah, actually, that's a good question. Why doesn't it come, yeah, that's a good question. Why doesn't it come with that? Yeah, that's a good question. Why didn't it fail for an instantiation? I think what you said was correct. Let's do another demo to illustrate this. That's not quite so complicated. Let's do cheap in and out. Now, any predictions here? Yes. And let's do cheap Joffrey's. Anything here? Okay. But now let's do expensive R. Yes, but now let's do cheap R. And what happens here? Well, based on our previous one, do you think this is going to be no, or is it going to be an instantiation error? Yeah, it's going to be no.
But is it no because of like that logic where it makes its instantiate X to Joffrey's? Or is it no because it doesn't instantiate at all? Because that seems...
How about this? Oh, we already did cannot prove X. And that, oh, that's a good idea. Shall we trace expensive R? Is that what we want to trace? Oh, cheap R. Right. We want to trace cheap R. So let's do trace, and then let's do cheap R. So it calls cheap, right? Then it calls cannot prove expensive with that same variable. Are you with me? Oh, and so then it calls expensive. Okay, that's calling the cannot prove expensive. So now it's calling expensive with that. Are you with me? Oh, now we see why it's going to work. And expensive succeeded, right? Because we exit. Because expensive Joffrey's did succeed, right? And then not that failed. Okay? So cheap failed. And that's why it's no. Did that answer our question? Did that was a good demo. Thanks for suggesting that. I should put that in my notes for next time. All right. So now here's the thing, you guys. There is a point to be made here. So let's go to the slides. Look, and I want to relate this back to what we do in formal methods with predicate calculus. Look, and it has to do with Generalized Demorgan, because you remember what Generalized Demorgan is? Remember that? It's kind of like, what's Demorgan? It's not A and B is what? Not A or not B. And then similarly, the other way, with not A or B is not. Okay. And remember that there is a generalized version of that with not there exists is the same thing as for all not. Are you with me on that? So suppose you have a database of facts that include all the good food restaurants and all the expensive restaurants, if any. Okay? The database represents a poor neighborhood. Are you with me on this? Of the good food and the expensive. Yeah, like we had before. The database represents a poor neighborhood if there are no expensive restaurants. Now, here's the thing. Prolog can determine the truth of this, of the left-hand side, but even though we know that this, according to predicate calculus, is equivalent to the right-hand side, Prolog can determine the truth of the left-hand side, but it cannot determine the truth of the right-hand side. And I want us to think about why that is. Because, see, if you say it's not the case, see, look, if you say it's not the case that there exists an R such that there is an expensive R, even if R is not instantiated, Prolog can search for the existence of an expensive R, you see, because it knows expensive. Because you're saying expensive here, right? With backtracking, if it succeeds in finding fact expensive Joffreys, it has proved that the neighborhood is not poor. If it fails to find any expensive facts, it has proved that if it fails to find, is my slide incorrect here? If it fails to find any expensive facts, it has proved that the neighborhood is poor. I think that's a typo on my slide. I mean, would you agree? So I'll fix this for the... Okay, but on the other hand, what about this? Why can't we do this? If R is not instantiated, because what is this? This is a for all R. Do you see? This is but what are R's? What are the R's? R's are the what? Are the restaurants. But what are the restaurants in our database? Those are those atoms. You see what I mean? It can't search atoms. It can only search for the, you see what I'm saying? It can't say for all R, not expensive R, and no, because here on the left it can search for expensive and match it and see if there's an expensive R, but it can't look at all it can search for the existence, but it can't search for all of the atoms that satisfy that. It does not have a set of atoms to use in its search. So look, you guys, what we're saying is that this is you can't. It's not exactly, you can't take your predicate calculus concepts and expect, you have to understand the limitation, you have to understand the matching, the searching limitations of how the search works to see that it's not as simple as just applying predicate calculus to Prolog. Do you see what I mean? There's a mapping that has to take place that's not one-to-one. Yeah? That's the point. Now I think it's really interesting for us to look at it this way because we know predicate calculus from formal methods. Yeah? Are we good? Okay, so that finishes that chapter. Now, were there any questions about, do you know now how to do the homework for today? What was that?
I think I'm still having trouble with set.
Oh, you have a question about set difference?
Yeah, but I was
okay.
about having known what we learned today.
Actually,
I was considering the definition of set difference.
Actually, it doesn't. I was thinking that today's would help us with the unifiable one on exercise 5.6. Yeah. So do you want me to give you some recommendations for set difference?
Yeah.
All right, let me give you some hints. This one's tricky, I'll have to admit. Okay, so what I recommend is this. Set difference. Now, let's think about this. Now, what are the three things? What are the three things in set? What are the three things in the set difference? It's the
set
first
1, set 2,
and set 3. And this is the difference. So the third one is the first one minus the second one, where minus is set difference. So the third, so how can this be this minus, well, look, what I recommend is, if this one is the empty set, then what? It doesn't matter what this is, the third one has to be the what? But specifically, what does the last one have to be? The empty set. Are you with me? Because it's the set of all the elements in here that are not in here. Well, there's nothing in here. So if the middle one is anything, then that one has to be empty. Are you with me?
Yeah.
Okay. Now, for my, let me set it up for you. Nyuk, nyuk. Set difference. All right, let me set up the parameters for you. I have two more rules. Okay. Maybe this will be guidance. Some good guidance. So here what I have is the key is how to set up these parameters, okay? Here if you say, I would say, you know, I think next year I'm going to always have this be first and rest. Whenever I have something as the first of a list, I'm going to call it first. So in keeping with that convention, what I'm going to say is first and rest 1, okay? And this would be list 2, and this would be list 3, if. And so the question that you have to ask yourself is, what has to be true for L3 to be the difference? What would it take for well, actually to be consistent? First one, rest 1. Okay. Okay. So what would it take for L3 to be the difference between the first one and the second one if the first list has a first and a rest? That's the question to ask. And then the second one would be set difference, and let's call this first one. No. This will be 1, 2, and 3. Are you with me? So this one would be first 1, rest 1, comma, and this one would be L2, and this one would be what? Actually, now this one we're going to make this just first. The same first. The same first and the same rest. If. What would it take for this to be, what would it take for this to be the difference between this and this if these were like this? Actually, now that I look at it, now that I look at the solution that I have, I think I have a single, oh no, they're not single because it's here and here. Yeah. Does that help?
I just wasn't thinking of it like that to begin with, so.
Yeah, maybe if you take a look at the way these parameters are structured, that will help you get the rest of the rule. And one of these has a member. One of them has a member and the other one doesn't. This one has two goals with member, and this one doesn't. This only has one. That's in some more guidance. 2 goals, one of which is member, only 1 goal. All right? So try that. All right. See you next time.